thank you for skipping your nap and coming earlier. Well, some of you may have your nap here, maybe. Depends on how exciting this will be. So I will continue with these lectures, and maybe I'll try to be a bit less overviewish than yesterday. Like maybe yesterday it was a bit too superficial. So I'll try to give more details, but on less things. I guess that would be better. So yesterday I told you that there are two important ingredients in generalization bounds. The one that I presented yesterday is the union bound, how to combine information about several random variables simultaneously. And the other ingredient is how to get information for each individual random variable about their deviation. So that's the deviation part. Here we'll dig a bit more into the deviation part. So yesterday I told you about this Hovding inequality, which essentially tells you that if you have a bounded function and you look at the empirical average and look at the true average, their difference will be of order 1 over square root of n. But actually, this is a crude upper bound, and you can refine it a little bit. So, okay, so the take-home messages of today will be that the deviations actually depend on the variance, and you can get a better estimate on deviation if you have a handle on the variance of the functions. And in particular, a way to get a handle on the variance of the function is via an estimate of the noise that is contained in your distribution. So if you have a distribution if your data is distributed in such a way that there is a small amount of noise, then the variance of the function will be smaller. And then you can get a better deviation estimate. So the noise is related to the variance. And we probably will skip the Rademacher averages part. We'll see depending on time. So how does this work? We have a function, and recall that this function f represents the loss of our classifier at a given point. Okay, so it's either 1 or 0. It's 1 if we misclassify the point, or 0 if we classify it correctly. So it's just a binomial random variable. And if we look at the sum or the empirical average of all these binomial random variables, we have a binomial distribution of parameter p. P is the expected value, and n is the sample size. So the expected value of the error is nothing but the expected risk of our function. So it's pf. Okay, so it's that simple. We have a random variable which is just distributed as a binomial with parameter p and n. And of course the goal is to estimate the fluctuations of this random variable. And actually it's possible to compute them exactly. So you can compute the probability that the difference between true and empirical error is larger than t for a fixed function. You can compute it exactly with this formula. But it's not very easy to work with this formula, especially when you have the next layer, which is to do the union bound. So if you want to do union bound with formulas like this, it gets a little bit messy. So instead, what we use are upper bounds on this quantity that are of exponential form. So here are several possible upper bounds. They are from the tightest to the weakest. And of course, Hovding is the weakest here. And there are several in between. And we will focus on the Branchline one, so this one here. So if we look, okay, so this is the probability that our deviation is larger than some t. And we noticed, the important thing to notice is that it's exponential, so it has a sharp decay rate, and it depends on the sample size n, here as well. And the Branchline upper bound also depends on p1 minus p, which is exactly the variance of the binomial distribution. So a binomial with expectation p has variance p1 minus p. So here is the variance. And so if we, okay, one way to interpret the exponent of Branchline inequality is to say, well, what happens when t is large or t is small? So when t is small, the dominating term in the denominator is the variance. So what we get is essentially a Gaussian tail with variance p1 minus p. So that's for small deviations, the binomial behaves like a Gaussian with variance controlled by p1 minus p. For large deviations, however, so if we take t large here, the dominating term will be the 2t over 3 in the denominator, which means we get a tail of this form here. And this is a Poisson kind of tail. So it's a bit heavier than a Gaussian. So this tells you that, I mean, somehow Höfding does not capture everything. And to show it a bit more, I have a picture here. And so here, what I have plotted is in blue, it's the exact formula for the tails. So this formula here, the binomial formula. And the other curves are all these upper bounds. So when p equals a half, so when the expected error of our function is a half, then this is when we have maximum variance. Recall the variance is p1 minus p, and this is maximum when p is a half. And in that case, all the upper bounds are more or less the same. Right? So all these curves, they are the Bernstein, Bennett, binomial, and what I call best Gaussian is this one here. So it's an approximate. This is not an upper bound, but an approximation. Okay, so you can say, well, in that case, I don't need to do any refinement. Höfding is fine. But now if we look at another situation where the expected risk is less than a half, like 0.1 here, then you see that the green one here is the Höfding bound, and the other ones are much sharper. The other ones take into account the variance, whereas Höfding does not do it. So this shows you that there is something to be gained if we take into account the variance, especially when we consider functions that have small error. And of course, the goal of learning is to identify functions that have small error. So these are the functions where we would really benefit from taking into account these refinements. Okay, so how do we do that? Again, for one fixed function, if we apply Bernstein inequality here, so we just take this upper bound here, and we mix it, we play around with it to write the bound in the standard way, which is here. And we use the fact that the variance, p times 1 minus p, is less than p. Okay. So if we use this, then we obtain this way of writing Bernstein inequality, which tells you that, as usual, the true risk is bounded by the empirical error plus here 2 terms. The first one being corresponding to the Gaussian behavior of the deviations, which is the variance, here upper bounded by pf only, divided by square root of n, plus a term which corresponds to the Poisson behavior, which is of order 1 over n. And this does not depend on the variance here. And of course, this will be the main term, especially when n is large. So as n goes to infinity, the dominating term will be the square root term. But this term, compared to Höfding, so Höfding, we did not have the last term, but the square root term did not have the pf as well. Okay, so here, compared to Höfding, okay, we have an extra term, but which is somehow negligible. And the dominating term has this factor square root of pf. So when the error is small, this term will be better. So the bound is better when the error is small. Okay, so now the goal is to translate that into, to use the union bound to translate that into a uniform statement over a class of function. And that's using the techniques that we had yesterday. Okay, one thing that I should mention as well is that you can massage a little bit this inequality, and that's a standard trick that is used in this business, which is to use, okay, I call it the square root trick, but it's a simple inequality. So notice that here you have an inequality that involves the error on the right-hand side. So that's not very convenient because you want to upper bound the error and you have a function of the error. So it does not really make sense as is. So what you want to do is to transform this into an inequality that upper bounds the error in terms of something of a function of the empirical error only. And to do that, you use this simple inequality here. So whenever you have an inequality of this form, x less than some constant times the square root of x plus some other constant, then you can prove that it gives you this inequality or also this inequality here. So that's actually that could be an exercise to prove it. It's not very complicated, but let's say the one who gives me the shortest proof would get say 5 points for the. There is a gift actually for the ones who get most points. I don't tell you what this is, but you will discover it later. So this is an incentive to solve this problem. Okay. So if you apply this inequality here, then to the previous result, then you get something which now looks like a bound where on the left you have the true error and on the right you have the a function of the empirical error. And now you notice that the square root term disappeared. So we have a 1 over n behavior. So in a sense, now we have a much faster rate of convergence, but of a different kind, because before in Hoeffding type inequality, we did not have this factor of 2 here, which meant that PF was converging to PNF at speed square root of n, but now we say PF converges to 2 PNF at speed 1 over n. So it's you can't say that this is better directly. It's better when PNF is very small. But if PNF is large, then you don't gain anything compared to Hoeffding again. Okay. Now, as I said, you want to convert that into a uniform statement. So the previous approach was to consider the difference between the true and empirical risk uniformly over the set of function by looking at the supremum over the set of function. Here, the problem is, as now we know that functions that have large variance will have big fluctuations in this difference, p minus pn, then when you look at the supremum, you will probably pick those functions that have large variance. So the supremum will be attained at the functions that have large variance. And that's not the functions that are interesting to you, because your algorithm is minimizing the empirical error in the hope that it will get a function that has small error, and as we know it, small error means small variance, hence small fluctuations. So in a way, this supremum is really not looking at the right functions. So what you want to do is instead rescale your functions. I mean, that's one trick that would allow you to get better results. And the way you do it is you normalize the functions by the square root of the variance. And you look, for example, at a quantity of this kind. So recall that the variance pf times 1 minus pf can be upper bounded by pf, and it's more convenient to use the upper bound on the variance than the variance itself. So that's why I normalize by square root of pf here. So now, if this quantity here is something that has a variance bounded by 1 for all functions, so all functions or all random variables of this type have the same variance. So now when I look at the supremum, I don't have this bias towards function of large variance. All functions are on the same scale in a way. So that's why I say here that normalizing takes into account the learning methods in the sense that it will not favor functions with large variance, which are not interesting for learning. It will put all functions in the same scale and in a way try to take into account the philosophy that we have in learning. Okay, so the type of result that we can obtain is of this type. This is an inequality due to Vapnik and Charbonnenkis, and it has the same shape as the ones that you have seen before, except that now the upper bound is on this relative deviation. And here the terms are the classical terms. So this is SF is the maximum number of possible vectors you obtain when you look at your function class on a data set of size 2n. So because you introduce this ghost sample. So this is what is it called? The shattering number. And you can upper bound this by the VC dimension. That's all you probably also know. So essentially, this would be like d log n, where d is the VC dimension and n is the sample size. Okay, so you get a bound of this form. And again, applying this square root trick, you can transform this bound into this form here, where you have an upper bound on the true error as a function of the empirical error, and you see that you have this 1 on n type term, and the 1 over square root of n, which is weighted by the empirical error. And you can also convert that into a bound where you would have 2pn plus a term plus this term only. So you can get rid of the square root term, but at the expense of putting a factor of 2 in front of the pn. So in a way, this is nothing but the bound that I shown before, but we combined with the union bound. I skipped this proof sketch, but now I want to notice a number of things on such a bound. So what is the best situation that we can imagine for learning? The best situation is when, for example, at least the target function that we are trying to attain, the base classifier, is in the class that we are considering, in the class G. Because at least we know that we may eventually find it. Right? So that's one thing. The other thing is you can assume that this best classifier, this target function, does not make any mistake, which means at any given point, the label can be either +1 or -1, but it cannot be a mixture of the two. It cannot be +1 with some probability and -1 with some other probability. So that's the zero noise case. And in that case, this target function does not make any prediction mistake. Okay? So these two conditions characterize this ideal situation. And in this ideal situation, if you minimize the empirical error, so if your Gn is the classifier that minimizes the empirical error, then its empirical error will be 0, because there is at least one classifier that has empirical error 0, which is the base classifier, but there may be others. So you're not sure, even if you have empirical error 0, that you have found the right one. And if you plug these things into this inequality here, which means you consider the function all the functions that have empirical error 0. So you put 0 here and 0 here, you get rid of those two terms, and the only thing that remains is this 1 over n term. So you can say that in that case, the true error of your classifier will converge at speed, okay, d log n, d is the VC dimension over n. Okay, and that's also something that John has shown you. In the zero error case, you get 1 on n convergence speed. And classically, people say, well, such a bound interpolates between the 1 over n rate and the 1 over square root of n rates, which you obtain when you don't have these ideal conditions. But the problem is, if you use these bounds to and look a little bit closer at what's going on, and you want, for example, to convert a bound that relates true and empirical error into a bound that compares true error of your classifier and true error of the base classifier, which is ultimately what would give you a guarantee of convergence to the target function, then you get something like this here, So you have the true error of your classifier upper bounded by a function of the true error of the base classifier. But if you look at this function here, you have the 1 over n term, fine, but you also have this square root term. And since this is a constant, this does not depend on the sample size, right? The true error of the base classifier does not depend on the sample size. This whole bound cannot converge at speed 1 over n. Because this is a constant, this term will never vanish unless the true error of the base classifier is 0, and that's the ideal situation. But apart from this situation, you have 1 over square root of n rates. So there is no interpolation in the sense that you either have 1 over n in one specific situation, and in all other situations, you have 1 over square root of n. And the reason is that we are not looking at the right quantity in a way. Because what may be small is not the error of the base classifier, but it's the difference between the error we make and the error of the base classifier. What we want is that the error we make converges to the error of the base classifier, no matter whether the error of the base classifier is 0 or not. So we have to look at differences of this form here. But the problem is we cannot really apply all these reasonings, all these bounds to differences. Or at least not the bounds that I've shown before. And there are refinements that allow you to take into account these differences, and I'll show you that in a minute. So I need some more definitions, but maybe I won't get into the details. Well, okay, let's just browse through this quickly. Okay, so there are things that you might recognize easily. Here, I call that the regression function. It's the expected value of the label at a given point. And you can write it as twice the probability that the label is positive minus 1. Now, the base classifier, so the ideal classifier, would predict exactly with the sign of this function here. So whenever the probability of being positive is larger than half, you predict with plus 1, and otherwise with minus 1. And in the case where in the deterministic case, so the case where the label is determined at any given point is when the random variable y is exactly equal to the target function at x. Okay? And in that case, you have 0 noise. But in general, you have some noise, and you can quantify the noise as a function of the points defined in this way. So essentially, it would tell you that it would be 0 when the class is deterministic, and it would be at most 1/2. And when it's 1/2, it means you have exactly probability 1/2 of being positive or being negative at this given point. Okay, so this is a function that is between 0 and 1/2, and it's defined over the whole space and depends on the noise that you have at the point. And it turns out that you can define conditions on this noise function such that when they are satisfied, you get rates that are in between 1 over n and 1 over square root of n. And the way to do that is to measure how often this noise function is close to 1/2, which is the worst case scenario. So in the worst case, you have a noise of 1/2 everywhere, and then you have nothing there is nothing you can predict because at every point there is no way to decide between positive and negative. That's the worst case. But in the best case, the noise function is 0 everywhere. But in between, you may have intermediate situations, and you want to measure how often the noise is reasonable. So one condition that you can set is that you may assume that the regression function, so regression function is 0 when you can't decide, and it's positive when it's easy to decide, and negative when it's easy to decide as well. And so if you impose that this regression function is larger than a certain constant, then it means you don't have this intermediate situation where the noise is close to a half. So this is equivalent to saying that the noise is bounded away from a half. So if you impose this condition, then you can have a fast rate of convergence. There are other conditions that you can put. Let's look just at the last item here. Those three things are equivalent, but let's just look at the last one. So what it says is that the probability that your regression function is small, so in other terms, that the noise is large, has to be bounded by some function of the size of the noise. So if you can guarantee that you have such a condition that holds, which tells you that the number of points where you have a large noise is small, then you can get a rate of convergence that depends on this alpha here. Okay, this is to prove that these three conditions are equivalent. And okay, let's see here. So how do we use these conditions on the noise? Recall that in the standard case, the variance is upper bounded by the variance of a function is upper bounded by the expectation of that function, at least when the function is positive and bounded, right? In the previous case, we had a function which was either 0 or 1, and the variance of such a function, it's easy to see that it's less than the expectation. But I told you that what is interesting is not to look at the loss of a classifier, but at the relative loss of the classifier, comparing the loss of the classifier with the loss of the base classifier. And now, if we look at such a difference, we have a set of functions, here the relative loss class, which are no longer between 0 and 1. And for such functions, you don't know whether the variance is bounded by the expectation, especially because the expectation may be negative, but still you may have some non-zero variance. So you cannot really use the same trick as before, but under the conditions that I mentioned, so under these noise conditions, you may also show that the variance is upper bounded by a certain function of the expectation. So provided you have this condition which is due to Tsibakov, that's why it's called Tsibakov condition here. So provided you have this, the noise is reasonable, then it turns out that the variance of functions in this class is upper bounded by a function of the expectation of the same function. Okay? So then you can use the same trick. You can use Branchline inequality and replace the variance by this, and you get a bound that upper bounds the true risk by a function of this true risk, and you massage it again, and you get this kind of result. So let's look at here. So this would be the first step. I use here the finite union bound, so the simplest version of the union bound, and Branchline inequality applied to these differences, Fn minus F star, and I get that this difference is upper bounded by the empirical version of this difference plus this term, which is variance times square root of n, and the variance I upper bound by the expectation to the power alpha, and an extra term here. And now I have to solve this inequality, which means putting this term on the left, and with an analog of the square root trick, but which is extended to any power. And I get this result here, provided that my best classifier is in the class. Because in that case, the empirical error of the empirical risk minimizer is smaller than the empirical error of the base classifier, which means this term here is negative, so I can get rid of it. So then I obtain the result here, which tells me that in the situations where the noise is controlled, so when I have a reasonable amount of noise, the convergence of the risk of my estimate to the best risk occurs at speed 1 over n to some power. And this power, when the noise is when the noise is 0, this power will be equal to 1. So that's the ideal situation. When the noise, when I have a large amount of noise, this will be 1 over square root of n. And in between, I can have any power of n between a half and 1, depending on how much I have noise. Yes?
Could you please repeat how to deal with the empirical error of the base?
Oh, here. Yes. Okay, so I make the assumption that this function here, f star, is in the class. Well, you don't really need to do it, but actually I skipped one slide which was explaining that. Usually when we look at the difference between the risk of our classifier and the Bayes risk, we first decompose this into two terms. One which is, a star is missing here. So one would be R of G star, the risk of the best function in my class, minus the risk of the Bayes classifier, and plus this term, which would be the risk of my estimator, minus the risk of the best function in the class. And this term is called the estimation error. This other term is called the approximation error. And this approximation error is deterministic. Like if I have a fixed class of function, then the best function in that class is a fixed function, and that I can compare the risk of this best function with the risk of the Bayes classifier, and this I will always pay at least this price. And then the extra price I pay here, which is the risk of my classifier, which is random, this is a random quantity, and that's the quantity that I want to estimate how fast it goes to 0. So that's why, in general, you apply it to a function which is the best in the class. So when we look back at this slide here, this condition is always satisfied when you look at the estimation error. So now, provided that f star is in my class, given that my classifier here is the one that minimizes the empirical error in the class, we are guaranteed that the empirical error of this one is less than the empirical error of any other function in the class, and in particular, less than the empirical error of this one. So this difference here has to be negative. So you can upper bound by 0. That's how you get rid of it. Okay, so maybe just a word on local Radmacher averages. To say that the Radmacher averages that you have seen before do not allow you to obtain a rate of convergence better than 1 over square root of n, because the bound are of the form, the difference between true and empirical error is bounded by the Radmacher average plus 1 over square root of n, and the Radmacher average itself cannot be smaller than 1 over square root of n, at least if you have, if you have at least one function in your class, that's the case. So to improve these results, you need to modify the reasoning behind the derivation of these bounds. And the modification you introduce is, again, of the same flavor. You, again, consider functions that have a small variance. And you introduce what are called local Radmacher averages, which are more or less the same. So this Rn of f, which I did not explicit, is the sum of sigma I f of xi. So it's the standard thing that occurs in the Radmacher averages, but the difference here is that you restrict your class of function. You only look at functions that have variance bounded by some constants. So that's why it's called local. You look at a small ball in your class of function, the ball of function that have small variance, and you consider and you compute the Radmacher average of this ball. And if you do that, you can get such a result. So, well, okay. Why would you be able to consider such a set of function? Again, you have to take into account the fact that you're looking at, or your learning algorithm is trying to find functions that have small error. So you can say, I have first some kind of crude upper bound. I know that the fluctuations of all functions in my class will be bounded by the Radmacher average over the whole class. So if you do that, then you know, you get an upper bound on the variance, or on the risk of of all your functions. And you can say, well, now if I look at the ones that has the function that has a small empirical error, then the bound corresponding to this function has to be small, because the bound is a function of the empirical error. So when the empirical error is small, the bound is small. So I get a good bound on the true error of that function. But then I can say, well, so if this function has a good upper bound, then maybe I don't need to consider the whole class of functions, and I can only consider those functions that satisfy this bound. And then you can say, well, then I can go back to my previous step and replace the Rademacher average, which was over the whole class, with the Rademacher average, which is over the class of functions that have a small error or a small variance equivalently. And then you can repeat this process. Of course, it doesn't work so easily. You have to, you pay a little price every time because you have some kind of union-bound process to perform. But you can iterate this process. And in the end, you have to balance the size at which you look at the functions and the Rademacher of this class. So, if you look at functions that have a small variance, then their expectation is bounded by this quantity here, computed at their variance. So you have to trade off between the variance of the functions and the complexity of the functions that have this variance. And this gives you what is called the fixed point equation here. So this psi here is this function here, the Rademacher of the function class at radius f. And you have to find the point where this function psi of r is equal to r star is equal to r star. And it turns out that this specific value of r is the quantity that controls the error of your functions. So the type of result that you would obtain, let's look at here, is that you can upper bound the risk of your functions by the empirical risk plus, and that's the complexity term, this r star, the fixed point of the local Rademacher average, to some power, which is related again to the noise level that you have, plus 1 over n, essentially. So that's how you get a result of the Rademacher type. Okay, so I guess that's it, and I can conclude here. Okay, so let's go back to the take-home messages. So as I said, the deviations are better when you take into account the variance, and one way to control the variance or to relate the variance to the expectation is via control on the noise level that you have in your data. And you can quantify this noise, and depending on how much noise you have, you can have better or worse rates of convergence. And to improve the bounds with Rademacher averages, the trick is to localize them by looking at small subsets of your class of functions, subsets where the variance is small. And that's it for this lecture. So we can have a break, 15 minutes break, and start at 4.